Thank you very much for the invitation, and it's a great pleasure to speak here. So before I start, it's a joint work with Bryce Orloski, my student at Penn State. So if I say I, it means we. Just to okay, so I'm going to start the talk by a basic question. So question number 1, which is I'm going to write it here. So what compact set? I'm going to denote compact set by sigma in this talk, subset of complex numbers and contain infinitely many conjugate algebra, infinitely many sets of conjugate algebraic integers. So I write algebraic integer. So, for example, so I'm going to give you 2 examples which are extreme odd. So example number 1 is basically unit circle S1, and it contains infinitely many sets of conjugate algebraic integers, the roots of unit. And its conjugates. And one thing to observe is that somehow it contains infinitely many, but the growth of them is not that large, so it's somehow linear in degree. So that's one thing to note, is that there are infinitely many, but the growth is somehow linear in degree. So that's something which we're going to be interested in. We really want to count at the end of the talk how many conjugate algebraic integers a set contains with respect to the degree. So this is the types of the theorems we're interested in. So we're also interested in the subset of real case. So when sigma is real, it's interesting from for example, if you're interested in studying the zeta function of a curve, so this case is going to be interesting. So if we look at the trace of an element here, we get basically the roots of unity are going to map to the interval -2 and 2. So we basically, there are infinitely many conjugate, let me call it Rn. So this is another example. Example 2 is the interval of real interval, right? It's subset of reals from -2 and 2. So both of them contain infinitely many, but what Fekete proved was basically these are minimal set, meaning that if you shrink this circle into smaller, or this interval into any smaller one, then you only have finitely many set of conjugate algebraic integers. So let me state.
When you say shrink the circle, you mean just take part of the circumference, or you mean a smaller circle?
Both of them. If you take part of it, there are only finitely many. Or if you take a circle with a smaller radius than 1, then it's and you place it anywhere in the complex plane. Same with the interval. If you shrink it or take any, or move it, translate it. So what is Fekete's theorem? So this is from 1923. So he defined the notion of transfinite diameter, which is the capacity of a set. Diameter of sigma. So how is it defined? So for each n, we find d sub sigma of n. We maximize the product of the pairwise disjoint distance. So if you pick n points inside sigma, and then we take the product of the distance between zi minus zj. So there are two choose n different pairs. And then we basically normalize it to basically 1 over 2 choose n. So that's going to be the so nth transfinite diameter, and the transfinite diameter is simply the limit as n goes to infinity of these d sigma of n. So one thing to observe is that if these are the roots of a integral, a polynomial with integral coefficient, this is with monic. This is going to be the resultant, and it's going to be an integer. So when we take this product, so with the roots, this has to be basically bigger than 1 if they're basically coming from roots of an if they're like a set of conjugate algebraic integers. So that somehow, that's a certificate necessary condition has to be whole, so which is d sigma has to be bigger than or equal than 1. And in fact, in these cases, d sigma is exactly 1. So d sigma of a circle of radius r is r. So this transfinite diameter has nice properties. It's scale with it's linearly scaled. So if you have a set sigma scaled with r, so the transfinite diameter expand with r, and that's a necessary condition for a set to contain infinitely many set of conjugate algebraic integers. Okay, so and let me write down the both theorem. So d of S1 is 1, d of interval of radius, d of an interval from -2 and 2 is 1. Okay, so the next question is a converse of this theorem. So that's due to Fekete and Siko, a version of it for complex plane. So let me state the theorem. So this is 1955. And what they prove is actually if you start with the set, compact set with transfinite diameter bigger than or equal than 1, the necessary condition, then sigma might not have infinitely many. But if you look at the epsilon, every epsilon neighborhood of sigma contain infinitely many. So by epsilon neighborhood, I mean, so I denote sigma sub epsilon to be the basically the points such that the distance of z minus somehow x is less than epsilon for some x inside sigma. So what they prove is basically if you fatten a little bit your set, then it contains infinitely many. Sigma contains infinitely many conjugate algebraic integers. Okay, so but for application to somehow algebraic geometry, I mean, if we start with this, we expand it, then it's going to actually go off the real line. So an important contribution was due to Robinson, which extend this theorem for real subset of real lines, but expanding with respect to real topology. So we stay in the real world. So I'm gonna write, this is Robinson's theorem, 1964, where he proved basically similar result, but we expand in with respect to real topology. Right? This sigma epsilon contain infinitely many. And one important basically property that Robinson used is the property of Chebyshev polynomial. So his proof is actually quite delicate to construct these algebraic integers. So he used the properties of the Chebyshev polynomials of a compact set. A Chebyshev polynomial is basically a polynomial of degree n which minimizes the maximal value on sigma. So in the case of -2 and 2, these are basically the trigonometric polynomials. So coming from writing cosine n theta in terms of cosine theta. But for general sigma, they're defined, but they're not explicit. So basically, so this is about question 1. Then I want to raise a different question where, let's say we have a set sigma which contains infinitely many set of conjugate algebraic integers. Then we are interested in how they're distributed inside sigma. So for example, in this case, they're going to be uniformly distributed. And that's the only limiting measure that you achieve by Kroneker's it's a classical theorem. Yeah. So basically, in this case, you also have a unique measure. And in fact, in the case when this sigma is 1, you always have a unique measure. And that unique measure is called the equilibrium measure of the set. So intuitively, it's so the way to think about the equilibrium measure is that you basically start a point far from sigma at infinity, then you do a random walk, and you see how it hits the boundary of your shape. So that measure is called the equilibrium measure. So in the case when this sigma is 1, basically, and Robinson construction gives you the limit, so basically the root distribution of these Chebyshev polynomials are also the equilibrium measure. So somehow Robinson construction gives you a construction which gives you a algebraic set of integers with limiting distribution of equilibrium measure. But then there was somehow a second question which I'm going to ask is the following: what are the, like other than the equilibrium measure, what are the other possible limiting distribution? Is there any or not? So this question, I guess, let me write it explicit. What are the limiting probability distribution of conjugate algebraic integers? So by limit, you have to just I mean the weak limit. So we say mu is a limiting measure if mu is equal to the weak limit of. So here I define some notation. If I write mu a polynomial, it means the root distribution of the polynomial, which is the following. So mu sub, let's say p is a polynomial, is defined to be 1 over the degree of the polynomial, sum over the delta mass at the roots of the polynomial. So it has n roots, and it's a measure, it's a probability measure supported on the roots of P. So we are interested in weak limit of along a sequence of polynomials such that all the roots of Pn belongs to sigma, right? So that's the question we're interested in. So roots belongs to sigma. Roots of Pn belongs to sigma. And actually, in order to be, so we're going to go with along this theorem, Fekete and Siko. So we restrict the roots to be somehow in epsilon neighborhood. But I write R. If I write R, I mean epsilon neighborhood with respect to real topology. So that's the question. What are the possible mu? So it's a more refined question than just knowing there are infinitely many. We want to know what statistics of it. And there is, again, like a necessary condition that was here. There is an analog of it for this limiting distribution, which I'm going to write down. So I believe this is observed by Smythe first, but Sir actually constructed a measure which satisfy all these necessary conditions that I'm going to write.
Did you check? I mean, I told you I think it's smart.
I think Smythe actually paper precedes the. I mean, Serle's construction is a letter to Smythe to basically after Smythe's paper, but I'm not sure. So perhaps someone knows. Yeah, can correct me.
Maybe Dimitrov. No.
Yeah.
That's Chris Smythe.
Yes.
Yes, I think you're right.
Yeah. Okay. So let me write down the condition here. So it's a positivity of log moments. So which is basically the following. For every test function which is belongs to z of x, so not necessarily monic polynomial. So these are monic. We're interested in the right roots of monic, but this one is not necessarily monic. So this has to be, this integral has to be positive, basically. The integral of log of absolute value of q, let's say x, against your measure. So let's call this measure arithmetic, the ones which are going to be the limiting measure of some algebraic set of integers. So the integral, the expected value of log of absolute value of x has to be actually positive for every test function qx. And the proof is again use the fact that the resultant. So the proof is basically easy, but somehow observing this should be somehow all the conditions. This is a big insight. I'm not sure if Smythe has this insight, so I would say Alex Smith. So you told me at this conversation with Smythe that actually his main contribution was to basically prove that these are the only necessary conditions. These are sufficient conditions. So let me write it. Let me write the proof for this. So the proof is actually the fact that if we take the integral of log of x against the root distribution of polynomial, we are basically taking the sum. So it's going to be 1 over degree of Pn.
I think the exact history is Smythe wrote this condition down, and Serle then asked, "Is this the only condition?" And Smith
Proved it. Yeah.
proved it for real. Yeah.
Yeah, for real cases. So basically, this is going to be this. The integral against this discrete measure is simply the sum of delta mass against the log of q, which means we are basically taking the sum of these log at the roots of En. But this is, we can write it as 1 over log of the product of the roots. But that's, as I said, is the resultant of two integral polynomials, which is an integer. So log of this. And log of a number bigger than 1 is positive, so it should be. And when you take the limit, basically you can derive this. So now we know what to look for. Basically, we have to have this positivity of log moments, and as I said, Alex Smith in the using basically the same. Using ideas from Robinson and using Chebyshev polynomials, he was able to prove basically that's the only necessary condition if sigma is finite union or countable union of intervals in the real case. So Smith. So let me write a Smythe here. And actually, Smythe use this moment inequality to improve upon Ziegel's bound on the average trace of a totally positive real number. So, but Smith basically proved if sigma is, let's say, finite union of intervals, then, and then, so let's call the measure satisfying this property B sigma, subset of basically all probability measures. Let's call the arithmetic measures A sigma. So Smith basically proved that A sigma is here. And Alex Smith basically proved the other way around. And they're basically
Sigma's got capacity bigger than 1.
I mean, both are going to be empty. Yeah, that's important. If this sigma is less than 1, then both sets are empty. That's actually not.
Yeah, that's bigger.
All right. So now I'm going to state our. So this is a result which is basically due to my student and myself. So we prove that basically without using the property of Chebyshev polynomials. And in fact, that allows us to prove something stronger, which I'm going to state. So a version of it is that if sigma is inside C, so imagine it could be some boxes and let's say some real intervals. So, but it should be symmetric by complex conjugation. Right? So because if you have any, that's a necessary condition to be symmetric. So if this is, then we prove basically A sigma is equal to B sigma. So in fact, there is so the result that is available for Chebyshev polynomial are not available for the complex case. So one important contribution of our result is to actually give a new proof of Robinson's theorem without using Chebyshev polynomials and its definitions. So we basically recover Smith's theorem and Robinson's theorem without using Chebyshev polynomials, and in fact we can extend it for accounting. So we want to basically the next question that I'm going to raise is going to be related to the observation that I made at the beginning about the number of conjugate algebraic integers like this converging to a given distribution. So for that, I need to define a notation which is basically important in our proofs, and it's basically not been introduced before. So it's a new definition that we denoted as a generic sampling and so now I'm going to talk about the proof of this theory. So the goal is the following. We are given a measure which satisfies this sigma, meaning that it satisfies all the positivity of log moments. So we want to construct a sequence of polynomials converging to that measure. And we want to actually count how many, for a given degree, how many polynomials have a root distribution close to sigma. So to make it quantitative, I need to somehow define this notion. So generic, so this is the assumption, the generic sampling of endpoints. According to, let's say, mu inside DC. So it comes,
Just to be clear, the statement here is that sigma is a union of products of intervals and intervals. and satisfies this. Then asymmetric.
Yes, if sigma is finite, let's say union, actually it's general. If sigma is any compact set, we have two versions. Then sigma epsilon, then basically A sigma is equal to B sigma. But I define A sigma in this definition.
You're allowing this, in other words, suppose I have a real union of intervals in the line.
Yeah, so I'm only allowing to expand them real wise.
Yeah, but suppose I have real and the capacity is exactly 1.
Yeah.
Can you force your roots to be in that set? I think
No, we can force them to be inside.
slightly bigger, slightly.
Yeah, but power saving, like 1 over.
Okay, I'm just saying the case of capacity 1, I think, is open. Probably.
Yes, that's right. Yeah, actually, that's a good point. So if you have an interval of length 4, we don't know if it has infinitely many or finitely many.
No.
Yeah, that's.
No.
Interval, not AB could be irrational.
Endpoints, right?
Arbitrary endpoints.
Like, with non-integer endpoints.
Yeah, with non-integer, yeah. That's right.
Yeah.
Yeah. So that's one complication. So it doesn't apply to this case. But if we largen it like with 1 over square root n, then we can.
Okay, so I mean, in terms of the set, as long
Yeah.
as the capacity is strictly bigger than 1, I think that was also in Robinson's work.
Yes, so that's why in Feket's formulation, they need to expand it. So they're equivalent. Either you start with D sigma strictly bigger than 1, or you start with D sigma 1 and expand it.
The reason I read, I think Smith asks this question in.
Yeah, that's open. Yeah, we don't have progress on that, but what we can do is to have a power saving, like we can prove it for sigma, let's say n to the minus delta. Or n.
Okay, just, can you just be clear about the hypotheses on this theorem?
My hypothesis is sigma is compact and is symmetric, then A sigma is equal to B sigma.
That's all you require is that. It's
Yeah.
compact, right?
Yes, exactly.
Okay.
But A sigma that I defined is has this condition that the roots are not necessarily inside sigma. They are inside, epsilon neighborhood of sigma, but epsilon with respect to the real topology. Okay, so now I want to talk about the proof. So this definition is, so what is this definition? So let's say we have a box, this sigma, let's say is a box. So we want to have a definition for like sampling endpoints according to mu. So mu is a measure defined inside this box, or it could be on the boundary. So we basically partition this box into m parts. So that's one parameter. So it comes with parameters m, l, n. So what does it mean? So we require we say Z collection of Z1 to Zn is a generic sampling of endpoints if it satisfies this property. So Z has to be symmetric by complex conjugation. So it could be all real, but if it's a complex non-real, the conjugate has to be inside Z. And then the second condition is that you count points inside each of these small partitions. So this is basically 1 over m. 1 over m. This, if this is unit 1. So for every Bij, if we count the number of points inside the this box minus the expected number should be bounded by an error term, which is L. So L basically is the discrepancy of our sample points against the expected. And then the last condition is that the points should not be like too close to each other, but that's somehow a mild condition in the sense that they're polynomially away from each other. So z minus w is bigger than n to the minus, let's say, 1,000. So they're not extremely close. For every z and w inside this z, yeah, that's the condition that we require. So, and in fact, if we just pick IID, it satisfies all these conditions, but we need to put some conditions on the range in which M and L vary. So M should be less than, you expect to have basically at most N partitions. So M should be less than n to the 1/2 minus epsilon, and bigger than n to the epsilon. And L should be also n to the minus epsilon times m to the minus half. Again, it's what you expect. You have n points, so the average value you expect to be n times m to minus 2, but you just take a power saving. So both of them are holds if you sample with IID independently. All right, that's the conditions that we need. And what we're going to do, we're going to actually use these generic sampling and then try to somehow deform them in a way to make the polynomial. So then I'm going to define, let's see.
So far, there's no integral polynomial.
Yeah, so far it's just discretizing the measure into somehow, yeah. Okay, so before that, I want to define two important quantities that show up in our proof in actually our counting formula. So one is called the energy, the logarithmic energy. So I of mu is going to be basically the integral of log of z1 minus z2 d mu z1 d mu z2. So you pick two random points and this expected value of the log of the distance. I mean, other context it's minus because they wanted to, but it's better for us to just don't use minus. And then you have a potential, which is basically for a fixed point z, you measure this. Basically, you take the expected value of log of the distance of z from a random point. So let me write this: log z distance d mu x. So this is called the potential function with respect to mu at point z, and the energy is simply just the average of the potential, right? Okay, so they show up in our counting formula. Okay, now I can phrase our counting formula. So the goal is the following. So we want to count the following. So let's say this is sigma, and let's say someone is given us a generic sampling with this property. So we have a point z1 here, and then we have a point, let's say z2, etc., zn. So we want to perturb these zi's inside the exponentially small neighborhood of z1. So that's where we're going to use this sigma is actually strictly bigger than 1. So the radius of this small ball around these generic points is basically d sigma to power minus m. So you should think about m is a a parameter, which is, think about it, is of size square root n. M actually could be anything less than n. So n to the minus delta also works. So we have, so in this case, it's like you're only allowing counting conjugate algebraic points, which are exponentially close to these generic sample points. But of course, that could not happen. For example, the trace might be non-integer, right? But if you allow only exponentially small perturbation, it remains non-integer. But what we allow is to have m auxiliary somehow noise points outside these balls. So let me explain the exact counting. So we want to count the set of monic polynomials belong to Zx. Monic such that. So the degree of P is fixed to be n plus m. And then the second condition is that Zi, so let's assume that P has roots. Roots of P, I'm going to denote them by alpha 1 to alpha n, and alpha n plus 1 to alpha n plus m. So the roots alpha 1 has to be inside this exponentially small ball. Alpha 2 has to be close to Z2. Alpha n is close to Zn. And then the rest can vary, but they're not, they're somehow square root of them. So they don't change the distribution of the roots. And in fact, they don't change the main counting. So the second condition is that for I between 1 and n, the roots has to be inside these exponentially small. So each one is one in each small ball. All right, this should be less than d sigma to power minus m. And the third condition is that the root has to be inside sigma. So I don't allow them to go away. So they have to be remain inside sigma. All right, so that's the J between 1 and. So the main theorem is that basically this counting formula is asymptotically given by this formula. So e to the n squared half times this energy. So in fact, there are many of them. Plus error term which depends on mn. So actually, it's going to be a power saving error term. But it of course depends on n, because you can't allow n to get close to n, because that's going to change the number. So an n squared minus. So that's the main theorem about counting integral
And of course, the Smythe condition comes in somewhere.
I already assumed that sigma belongs to B sigma. Yeah, so that's the theorem. If you assume the Smythe condition, then any generic sampling.
Your proof uses that.
Yeah, it's crucial.
Yeah, so we want to see how you use that.
All right, so I guess for the rest, I'm going to talk about the. Okay, maybe one application of this theorem for counting isogeny class of Abelian varieties. So, for example, we can use it to restrict the Frobenius eigenvalues to be exponentially small to a given. So let's say we have a circle of radius square root q, and let's say we we start with equilibrium measure, which belongs to this B sigma, the uniform measure. Then you sample n points. And then you put the size. Now, as I said, I mu in the case of uniform measure is square root q. So you allow q to power minus m intervals around them. So basically, the theorem says that there are isogeny class of Abelian varieties which are inside this exponentially, which has basically these Frobenius angles given, and then you allow m like exceptions outside. So if you let m grow, then these you can shrink this. So that's the interplay, right? So if you let m grow, you can shrink them more, but there are more exceptions that you don't know how to handle. So that's somehow the intuition between this auxiliary parameter m and the size of this shrinking box. Okay, so let me now talk about the proof, and maybe I make a remark about this exponent. So in fact, in mathematical physics, there is a...
Just back to your application, because that's the number theory part of it for some people.
Yeah. So maybe I write it explicitly. So let's say there are, so in this case, e to the n squared half times the log of q. So it's going to be q to the n squared divided,
Q is a fixed prime power, right?
q is a fixed prime, yeah. A fixed q, a prime power. And then given n theta 1 to theta n, just somehow weak, uniformly distributed in this weak sense. That you only allow just what the weak sense means, that you have power saving for discrepancy. So if you sample IID, you have square roots saving. Given theta 1 power with power saving and discrepancy. Then the number of them, there are q to the n squared 4 over 4 isogeny class Abelian varieties of dimension. Let's say you can put the ordinary condition here. The proof allows Abelian varieties of dimension m plus n. So you can control n angles, but the m of them could be anywhere, right?
What is d in this case?
D sigma is log of square root q. So D sigma is okay. D sigma is square root of q. I is the log of D sigma. So basically, e to the log is going to be D sigma. So in this case, the main term is q to the n square over 4. So there are basically plenty of isogeny class of Abelian varieties such that the Frobenius angle, Frobenius eigenvalues angle, so Frobenius angle is close to, basically exponentially close to this given theta.
To be clear, you can take your subset sigma to have capacity bigger than 1.
Yeah.
Then you can do this, and the points, your outliers, will also lie in that set.
Exactly. Yeah.
In other words, most of them lie when you want
Yeah, these points are still gonna, that's how we guarantee it's coming from Abelian, right? They lie on the, I mean, we use Naser theorem too. But yeah, so that's very important that we restrict these outliers to remain in the third condition, right? Yeah.
Are you using Honda Tate in a serious way? I mean, is there anything about Abelian varieties coming in here, or is this just a statement of about Weil polynomials?
It's really a statement about Weil polynomials, yeah. But in somehow geometrically, it means we can, make angles exponentially close to given points. Okay, so maybe for the rest of the talk, I'm going to talk about the ideas which goes into the proof. Okay, so let me erase.
But sorry, yeah, go ahead.
At some point, this exponent I will come out positive. Is that not?
Yeah, that's actually a good point. The fact that I is positive, I mean, allows us to show there are, I mean, if it's negative, then it's actually, the theorem holds, like if it's negative, none, yeah.
But under the Smith positivity condition, that actually already implies.
That's right, yeah. So in fact, one ingredient is actually, like one step in the proof is to prove actually I is positive, but in fact, generalizing it. So I'm gonna actually write.
Positivity conditioning multiple variables to say.
Yeah, that's what goes into the proof. Okay, so let me talk about or maybe I state what just mentioned. So actually an important, this is due to myself and Orloski. So it's an important input is that if we start with a measure inside the sigma, which means that the integral of log of qx, the mu is positive for every q inside the x. Then, so in fact, this condition alone is an analytic condition. It implies something stronger, which actually is crucial in our proof. So if you start with any degree, any polynomial in d variables, and take this somehow higher moment, so you pick basically x1 to xd IID, and you average it, then you also get positive. Actually, the proof is not, it's actually not trivial, but somehow it implies I is positive by taking q of x and y to be basically x minus y. So in that case, it implies I mu is positive. So somehow it's a higher version of a resultant. So that we are computing here. So it comes in actually in a geometric way. This allows us to control this convex.
Smith was never using this.
Yeah. So he didn't use this. He used a different input, a flatness theorem in convex geometry, but yeah, so our proof is different from, I mean, Robinson's input was also, so there are two important distinctions in our proofs. One is the use of introducing this condition, and one is we don't use actually Chebyshev polynomial, we rather use this generic sampling, and we sample with respect to equilibrium measure. That's how we substitute the Chebyshev polynomial input. Okay, so let me just say a few words about the general ideas that goes into the proof and how we use it in our proofs. Okay, so the proof is based on geometry of numbers. So we already discussed some generic. Okay, so let me say a few words about the proof. So we define this case of n, a convex subset of real coefficients polynomial, which is degree of P should be less than n. So it's a subset of Rn plus 1. And then we have this condition that the sup norm of Pz should be less than the normalized potential, n to the u mu z. Right, for every point in the complex plane. So basically, for every point, you have a value which is e to the n times the potential. You look at the space of polynomials such that for every point in C, they're less than this e to the n u mu z. So that's going to be a convex set. And our proofs is actually about proving bounds about the shape of this convex set, about the maxima, the Minkowski's minimum associated to this Kn. So let me say, so first, okay, so the idea is that what's the property of this Kn? It's a theorem that if your polynomial is monic and bounded by e to the n mu z, then its root distribution converges to mu. I mean, in our counting, we don't need this, but that's how actually Smith proof is resolved. So we don't use that input, but we rather use the set to construct polynomials here. So the goal of our proof is to show that Kn intersect with these Pn's as actually contains some lattice points. So we want to prove Kn is large, the volume is large. We are using Minkowski's theorem. So we need two inputs. We need to show that Kn is large, and we need to show that Kn is not skewed. Right? You might be like a large complex set, but you don't have any integral point other than 0. So we need those two. And let me see. Okay, one input is that first we prove that this generic so let's define P sub z to be the basically P sub z of x is basically the polynomial with roots given by these sample points. So x minus 3i. So in order to prove that the volume is large, we actually show that there are many, every sample polynomial belongs to Kn. So that's how we prove the volume is large. And since Kn is convex, then we just use the linear combination of them. So that's how we prove the volume is large, basically. So we prove that this belongs to e to the. So, and the key is that, in fact, we only need to save exponent should be any sub-exponential exponent would be fine. So that's some of this proof is, we prove this result. For some sub-exponential exponent, it belongs to Kn, if you fatten K. So using this, we can prove that basically there are points inside Kn and the volume is large. So this implies volume of, I mean, you need to reduce it to a van der Monde determinant and then do some estimate, but that basically implies the volume is bigger than the exponent that we wrote with the power C. So basically we know the volume is large because we can sample points. But then the other input, as I said, is to show that the shape is not skewed. It's not, we want to rule out this case. And that's where we use the condition. You have to use it somewhere, that mu belongs to B sigma. So in fact, if you start with a single polynomial, you can show that lambda 1 is, so basically the idea is this, if you start with a measure in B sigma, you can show that if lambda 1, lambda 2 to lambda n are the Minkowski's minimum, what we need to show is that this also grows sub-exponential. But the input B sigma only proves a lower bound for lambda 1, which is of the form e to the minus n half I mu. and extending what I just erased to a higher moment allows you to control actually lambda 1 to arbitrary lambda n. So you give it a lower bound. So it means that, so that's what I said, it's about like extending to higher dimension. It's really about controlling the minima at the same time. So this basically the higher moments positivity of higher moments implies that basically Kn is well rounded. It's not skewed. And okay, so now I want to put these two together. Basically, the idea is now to start with PZ and make it basically integral. So there is another input goes into the proof. We need to somehow amplify the PZ with using those outside points. So the initial idea is this. So now let's say I start with the PZ. Then you want to make the coefficients to be real, to be integer. So the idea is that, okay, I mean, if this is PZ and if you have a nice Minkowski function, you write PZ in that Minkowski function and just take the floor of those coefficients. But this doesn't work well in controlling the roots, because now if I do that, the roots may just change and follow a different distribution. So you need to somehow stabilize PZ first. So when you add, let's say, a linear combination of these Minkowski's basis, it doesn't change the roots much. And the idea is actually simple. So I say that's Robinson's idea, perhaps. So his main observation was that if you have somehow a function which is positive here, negative here, then you have a zero inside somehow. So, but if I start with a function which is large and I perturb it, it remains positive and negative around. So this doesn't work quite well. You need to multiply it with that outside root outliners. And Robinson's idea was to use the Chebyshev polynomials, because there's somehow a Chebyshev polynomial is exponentially large on almost all points. But you need to, when you multiply, you want to make sure that the top coefficients, now you have, you know, m new coefficients. So you can actually multiply to make those coefficients remain integer. And then use this trick to take the floor of the lower coefficient. So that way you can control. And basically, again, as I said, the proof, this is somehow gives you a lower bound on the proof. So with this, you can actually construct these many polynomials. The upper bound use a discrete version of John's theorem, meaning that you need to approximate your shape, your convex shape with a ellipsoid or a box. So that there are two inputs which we use. So John's theorem is also somehow new. So Smith doesn't use it, but it's crucial in getting the asymptotic bound. Okay, I hope I give like some ideas of the proof. I'll stop here.
Question?
I have a question. You started mentioning something about mathematical physics.
Oh yeah.
I forced him to remove it.
Yes, but maybe you can say a few words.
Yeah, so I wanted to say this density function is actually predicted by a model problem in mathematical physics, which is, I mean, we don't use, our proof doesn't use it, and I don't know if it's any like use in the other direction, but I just, this observation, if you have a, so there is a like a Coulomb's law in 2D, which is has the potential basically function is going to be minus log of x minus y. And then it associates to a configuration of n points, a potential function. So let me write it h of x1 to xn is going to be minus sum of, let's say, 1/2 of log of xi minus xj. So that's the potential function. If 2 points are extremely close, they're going to be blow up. So it's going to be a large. So then the prediction is that so the probability that observing these n particles with this potential is going to be given by e to the minus beta, so it's the inverse temperature times the times this potential function. And basically, this is going to match with our formula. Basically, the frequency of observing a conjugate algebraic integer following position x1 to xn is basically what is what is predicted by this law in statistical physics. So what is the corresponding beta is actually 1 in this case. So that basically gives the main term of the prediction. Yeah, so the understanding these coefficients are also important. So I have some guess about these coefficients. So I believe the coefficient of mn should be related to log of x minus y, b mu x, the equilibrium measure y. So somehow you intertwine both. So, but I mean, I don't have a proof, but it's just somehow these coefficients could be computable. Yeah.
I have a question. Well, yeah, Nina.
When you say coefficients, you mean an effective constant, or you think it's literally an exact formula?
So the coefficient of mn depends on shrinking size 2. So it gets affected by 2 coefficients. So if I don't make them that small, I believe like the coefficient should be similar to. So the idea is that if you just pick m and n with the same distribution, then the coefficient here should be n plus m squared, right? So when you expand it, you actually get this but if you change, so it's I believe it should be doable to get this explicit so I get them somehow the main term is a binary form in m and n. So I get the main term if I let n to be extremely larger than m. So the question is counting like polynomials with with roots, n roots following mu, m roots following a different measure.
So I do have a question in connection with Sarah's work, which was to say what are the possible intervals in which you could put your Weil numbers or your Frobenius. So he shows using Robinson basically the capacity, if you're a subset of the circle with capacity bigger than 1.
Yeah.
Then there are infinite sequence of Abelian varieties over FQ, whose Frobenius lies in that set. And that's a necessary condition and essentially sufficient. Now, the next question is, what is the possible limiting distribution on the circle of Weil numbers of and what you're showing and what Smith and you are showing is that necessary and sufficient condition is this extra condition of Smythe.
Yeah.
But do we know anything about these measures? Can you tell me which measures can be limit measures in this way other than that condition? In other words, the beauty here was that that condition is necessary and sufficient, but is there any conjecture as to what measures are weak star limits of Frobenius?
Coming from curves or general? Okay.
In general or curves? I mean, so for general, it's easier.
Yeah, for general, that's the condition. Okay, if it's
Yeah, but if I give you a measure,
yeah.
I mean, can you?
So-
it's still an infinite set of conditions that are very.
Yeah. So, okay, the one idea is that if your measure is positive everywhere, then it is a measure. Because, okay, let me write.
Yeah,
It's
yeah.
actually, yeah.
That sounds good.
So,
And that uses this theorem.
yeah, so if you take the integral of log of qx d mu x, then you can basically write it. It's basically the sum of potential function of mu evaluated at roots of q. So it's basically a finite sum.
Like a Mahler measure.
Yeah, so if you know your potential function is positive, yeah, everywhere, that implies
That you are able to.
and in fact, this holds at like if you are far from your sigma, because u mu of z is roughly log of absolute value of z.
Yeah, so far away it's true.
Far away is true, near. So one trick is that for the equilibrium measure, this has a positive lower bound. It's actually bigger than d sigma all the time. So if your measure is not positive, you can mix it with this u mu, so to make it positive everywhere. So somehow, so basically, if you have a candidate mu, and you calculate mu, and it's basically, if it's positive, it's good, you're done. If it's bigger than minus c, so then you can basically mix it with this measure. And actually proving this is an explicit problem again. So in one of application, I basically started with the mu and I prove basically everywhere it's positive. But of course, there are examples where it's negative. The condition is that the integral, so it looks like this. So the integral of the function is positive because I mu is the integral of the measure. But the function itself may oscillate. D mu c. So this is always true, but at those points where it's negative, then yeah, so you might be, yeah. You may, yeah, mix it with a measure which makes it positive. Yeah, so one thing about these measures is that they're conformally invariant. So if you're positive, then you apply conformal math, then it is going to be. But conformal invariant doesn't work for this arithmetic measure.
All right. Since we want to take a break, we want to start at 4, so that we actually finish at 5 and then still have time to talk. So I'll call it your end of your talk. Thank you very much.